All right then. So let's continue. As I said, so we are again dealing with Booth's multiplication algorithm. Whew. Okay, so let's do our next amazing big bucks question, which is 6 times 3. Actually, this is specifically minus 6 times 3. What is that? Right? How do you do that using binary and whatever nonsense? So let's get started. I already had the rules written earlier, and I kind of explained it in the previous example. So we'll just kind of continue. There's no need to actually do any extra setup here. So the m here is, now notice this is very interesting because here it is minus 6, right? So the m itself is negative, which is fine. Again, it's okay. Now notice how, this is what I'd recommend. Now if you're directly, you look at m and you say it's a negative 6, do not start with the 2's complement directly. Instead, find the minus m. What is minus m? Minus m is a 6, right? Now how do you write a 6 in binary? So 0, 1, 1, 0, right? 4 plus 2 is a 6. Now you find the 2's complement. So first we take the 1's complement. So 1, 0, 0, 1, add a 1, and you will basically get 1, 0, 1, 0, right? That is basically what it is, right? That's how that is done. This is the safer way, because if you make a mistake here, everything you did, complete waste. So Q3, that's a very easy to write number. That is what it is in binary. Now let's get started. So you'll notice how everything is in 4 bits. So that is amazing. So the accumulator has 4 bits inside it. We'll copy the Q 0011. The size of Q is 4 bits. So we have to run 4 iterations actually. Whoops. I forgot to write the Q minus 1th bit, which will be 0 by default. And then of course, since the size of Q is only 4 bits, we'll write 4 here. We'll say that we have 4 iterations to go. Let us begin the first iteration. So we see a 1 and a 0. Of course, what do we have to perform when we see a 1 and a 0? We have to perform a is a minus m. So that then is 0, 0, 0, 0. And what is a minus m? Now notice, do not go for, don't reason that, okay, minus 6 is m, so I can simply do, no. Minus m is minus m, not minus 6. Don't think like that. So minus 6 is what 6 is, and that's what we are supposed to add. So 0, 1, 1, 0. Okay, again, remember, minus m is what we are using. So 0, 1, 1, 0 is what the value will be. Awesome. So we'll write that intermediate step here. 0, 1, 1, 0 is what we have. Q stays the same. There is no change there. Q minus 1 stays as is. Okay. Now, in order to end this whole iteration, we have to perform a right shift. And that leads to, again, notice that this is a positive number. So we'll just write a 0 here to represent that. And then we'll perform the right shifting. 0, 1, 1. 0, 0, 0, 1, and the Q minus 1th bit becomes a 1. And now we say that we have 3 iterations left. Now notice how this is a 1, this is a 1. Both of these bits are the same. Now what do we do when the bits are the same in Q0 and Q minus 1? Nothing. You actually simply just perform a right shift and end the iteration. There is nothing to do here. So what does it become? So 0, so we keep that, and then 0, 0, 1, and then you have a 1, 0, 0, 0, and you have a 1 here. Now we say that we have 2 iterations left. Notice, so you have 0, 1 now. 0, 1 implies a becomes a plus m, right? That's what that implies. So you say 0, 0, 0, 1. Now you have to add m. Remember, m is minus 6. Doesn't matter, but it is m. So 1, 0, 1, 0. You add 1, 0, 1, 0 to this. There is no question to be asked here. Right, so that is the value 1, 0, 1, 1. So the intermediate value now is 1, 0, 1, 1. 1, 0, 0, 0 sort of stays inside the register anyways. 1 is as is. And now in order to end this iteration, we have to of course perform the right shift. Now notice how this MSB here is 1, so we just copy that and then perform the shifting 1, 0, 1, and then 1, 1, 0, 0. The 0 goes outside, that becomes the Q minus 1th bit, and now we say that we have only 1 iteration left. Amazing. And guess what? This here is a 0, this here is a 0. That means both of these values are actually zeros. And therefore, when you have the same bits, you do nothing, right? You simply perform a right shift and you end this particular iteration. So you have a 1 here, and you perform the right shift now. So 1, 1, 0, 1, 1, 1, 0, and of course the Q minus 1 bit is going to become a 0. And now you will say that you have 0 iterations left. Okay, this is your answer. Great. Now let's look at it. 1, 1, 1, 0. 1, 1, 1, 0. This is the answer apparently. Now notice one very important thing here. Now if you start converting this nonsense, one thing that people will immediately do, and even I did it the first time I did this whole numerical, is that you'll actually notice this bit. So again, what is it? 8, 16, 32, 60, 128. So you look at the MSB, you'll see that it's a 1 and you'll immediately say 128 plus 64 plus 32 plus 8 plus XY. You know, you'll do that. Completely wrong. That's not what that means. No. In fact, the moment you see a 1 in the MSB in the final result, that means that you now have to take the 2's complement of this value as well. So what was the value? 1, 1, 1, 0, 1, 1, 1, 0. So first we take the 1's complement. What is the 1's complement? 0, 0, 0, 1, 0, 0, 0, 1. Now what do? You add a plus 1. You add a 1. So 1 plus 1 is a 0. That becomes a 1, 0, 0, 1, 0, 0, 0. So the final answer actually is this whole nonsense. So 0, 0, 1, sorry, 0, 0, 0, 1 and 0, 0, 1, 0. And what is that in binary? So let's see. So 1, so you write 2 plus 4, 8, 16, right? So that is what it is. So 18. But remember that the original answer was a negative value. So you have to put a negative sign as well. Okay. Now let's look at what the original question was. So the original question was a minus 6 into 3 is equal to minus 18. Right? That's what that is. Right? So that basically is it. You know, and that you would write in binary as 1110, right? That basically is what it is. So yeah, that is basically about it. That was the Booth's multiplication algorithm, a very fun mechanical procedure, and that's about it. See you maybe when I do restoring division or something else, I guess. That's about it.